Welcome to the office. We want to take a look at a certain class of groups now. So the class that we're interested in, or a collection of them, is groups that have the quality of being commutative, right? If the operation is commutative. So a group is called abelian if its binary operation is commutative. Awesome. We know a lot of examples of abelian groups. For example, if I were to take the integers under addition, that is a group, and we know addition to be commutative. Now, we know that multiplication under the integers is commutative, but that's actually not a group because inverses don't exist. An identity does, but inverses do not. So there's an example that's not a group, fails inverses. What else? So we also know that under the real numbers, multiplication is abelian, and there's no real issue there. Multiplication, yeah. So actually here what we do is we do our star. We have to remove 0 because there's no inverse of 0 under multiplication. So all real numbers without all real numbers except 0, that is, under multiplication is an abelian group. We know multiplication to be commutative. So we know lots of examples of commutative groups, even the group of units and within the complex numbers, right? Or the roots of unity. We talked about those a couple videos ago. So we know plenty of examples of abelian groups. Now, what you might be more interested in are things that are not abelian. So we talked before about things like subtraction. Subtraction is not commutative. Well, it's also not associative, so that would fail to be a group, right? No matter whether you're talking about the integers or real numbers or rationals, that sort of thing, okay? So there's plenty of issues with subtraction. So if subtraction isn't good, and we know that addition is always commutative, we know that multiplication is always commutative, well, what in the world could it be? Well, we're overlooking some things because multiplication is not always commutative. In particular, if we consider the set of n by n invertible matrices, this is called the general linear group of size n, order n might be the right word there. I think I might even, they have that in here, general linear group of degree n. Also, and I apologize, they want R here. So general linear group of degree n with real entries. So that's the set of n by n invertible matrices with real, sorry, n by n invertible matrices with entries in R. Fantastic. So general linear group, degree n. Fantastic. It is a group, but it is not abelian. Matrix multiplication. So matrix multiplication. Let's see here. Matrix multiplication is not commutative. So again, this is an example of a group, or rather, if we say GL, general linear group, degree n, with real entries under multiplication, right? Matrix multiplication is a group, but it is not abelian. Right? That operation, matrix multiplication, is not commutative. We know that to be the case. Now, there are some instances where it works out, but in general, it does not. All right, so real quick joke here for you. How many commutative groups are there? How many commutative groups are there? A billion of them. Oh, okay. Yeah. If you didn't laugh at that, that's okay. I don't blame you. Anyway, we've got a little bit more to talk about within groups. So join me for more on groups. I'll see you back here in the office in just a minute.